Assalamualaikum and hello everyone. We are group 5 from class RAS 2131B. We'll be presenting about circuit analysis in household electronic devices.
Introduction. Household electronic devices such as televisions, electric fans, washing machines, and microwave ovens rely on electrical circuits to function properly. Circuit analysis is the process of studying how voltage, currents, and resistance interact within a circuit. By understanding circuit analysis, we can identify faults, improve device performance, and ensure electrical safety. This presentation explains the basic principle of circuit analysis and its application in common household electronic devices.
I will explain about the background theory of circuit analysis. First, what is circuit analysis? Circuit analysis is the study of how electrical quantities such as voltage, current, and power behave in an electrical circuit. This helps us to understand how different components in a circuit work together and how electricity flows through the system. It is important in electronic because it allows engineers to design devices that can operate safely, efficiently, and reliably. In our daily life, circuit analysis is applied in many household electronic devices. For example, devices such as television, washing machine, refrigerator, and rice cookers. Next is basic electrical principle. First is Ohm's law, which is represented by the formula V equal to IR, which shows the relationship between voltage, current, and resistance in a circuit. This law is commonly used to calculate electrical values during the circuit analysis. The second principle is Kirchhoff's law, which consists of KVL and KCL. Kirchhoff's law proves that the voltage around the closed loop is equal to zero, while Kirchhoff's law explains that is equal to the current within the junction. This slide shows the main electrical component used in electrical circuit. First, the resistor controls the flow of current and protects other components from existing current. Its unit is ohms. Next, the capacitor stores electrical energy, smooths the DC voltage, and reduces voltage reflow. Its unit is farad. The diode allows current to flow in only one direction. It also converts AC to DC and prevents reverse current. The transformer steps the voltage up or down and provides electrical isolation. For example, it can convert 240-volt AC to a lower AC voltage. Lastly, the voltage regulator provides a stable DC output and prevents voltage fluctuation, such as maintaining a constant 5-volt DC. For the circuit operation, I will use a phone charger as an example. The process begins when a charger is connected to a household power outlet by supplying 240-volt AC. First, the transformer reduces the high AC voltage into a lower AC voltage suitable for electronic circuit. Next, the current passes through the bridge rectifier, which converts AC into pulsating DC using diode. After that, the filter capacitor smooths the pulsating DC by reducing voltage ripple, producing a more stable output. Then, the voltage regulator maintains a constant output of 5-volt DC, even when there are small changes into input voltage. Finally, a stable 5-volt DC is supplied to the mobile phone, allowing it to charge safely and efficiently. Overall, this circuit shows how household electronic devices convert high voltage AC into stable low voltage DC using different electronic components work together.
Okay, now let's look at the actual math and data to prove how our phone charger works. First is the transformer stage. We start with 240 V coming out of the wall. That is way too much power for a phone, so we use a transformer with a 20 to 1 turns ratio to step it down. By dividing 240 by 20, we get a safe 12 V RMS. But waves have peaks. If you look at the first graph on the top left, the electricity is still a smooth wave moving up and down, reaching a peak height of 16.97 V. Next, the electricity hits the bridge rectifier. Remember how our first wave goes below the zero line into negative territory? The rectifier flips those negative loops upward. Now electricity passes through two silicon diodes here, and each one takes a small toll of 0.7 V. So we subtract 1.4 V total from our peak. As you can see in the top right graph, our wave transforms from an up and down wave into pulsating DC, which looks like a row of bouncy camel humps peaking at 15.57 V. But those bouncy humps are still too bumpy for a phone. That brings us to the filter capacitor stage. Think of the capacitor like a tiny water tank. When the wave goes up, it stores power. When the wave drops, it releases it to fill the gaps. Using the formula with a 0.5 A load current and a 1000 microfarad capacitor, we calculate a peak-to-peak ripple voltage of 5V. Look at the bottom left graph. Instead of dropping all the way to zero, the capacitor smooths the bumps out into a slight zigzag wobble. Finally, we reach the voltage regulator stage using the IC7805 chip. At the absolute lowest point of that zigzag wobble, the voltage drops down to 10.57 V. So here is the golden rule for the specific chip. To give us a clean 5V output, it needs an input of at least 7V, and we call this the dropout requirement. Since our lowest point is 10.577V, we have plenty of breathing room. So the graph on the bottom right proves that the chip easily shaves off the wobble, leaving us with a perfectly flat, safe, and stable 5V DC line ready to charge the mobile phone.
Next, I will explain the advantages and limitations of circuit analysis in household electronic devices. First, let's look at the advantages. The first advantage is that circuit analysis helps detect electrical faults quickly. This allows technicians to identify damaged components and repair them before the problem becomes more serious. Second, it improves device performance. By analyzing the circuit, we can make sure the electrical components are working efficiently, which helps the device operate properly. The third advantage is that it enhances electrical safety. Circuit analysis can identify issues such as short circuit or overloaded circuits, reducing the risk of electric shock or fire. Next, it reduces repairs and maintenance costs. Detecting problem early prevents major damage, making repairs easier and less expensive. Finally, it supports reliable device design. Engineers use circuit analysis to design household electronic devices that are more stable, efficient, and reliable for everyday use. Now, let's move on the limitation. The first limitation is that complex circuits are difficult to analyze. Modern household electronic devices contain many electronic components, making the analysis more challenging. Second, it requires technical knowledge. A good understanding of electrical circuit and electronic component is needed to perform accurate analysis. The third limitation is that specialized testing equipment may be required. Tools such as multimeter or circuit testers are often needed to diagnose problem correctly. Another limitation is that hidden faults can be difficult to detect. Some problems only occur under certain operating conditions, so they may not be immediately visible during testing. Lastly, circuit analysis can be time-consuming, especially when troubleshooting advanced electronic devices with complex circuit design. In conclusion, circuit analysis offers many benefits, such as improving safety, performance, and reliability. However, it also requires technical skill, proper equipment, and sufficient time to analyze more complicated electronic systems.
Now, I'll be presenting the real-world application of circuit analysis in household electronic device, focusing specifically on AC to DC power adapter, commonly known as your phone or laptop charger. Every day, we plug device into our household wall socket. We supply 240 volt of alternating circuit. However, the internal microchip of our smartphone requires a steady, low voltage direct current, typically around 5 volt, to operate safely. This transformation relies heavily on the core analog electronic principle we analyzed in our report. First, a step-down transformer decreases the high household voltage. Next, the low voltage AC passes through a full-wave bridge rectifier composed of 4 diodes, flipping the negative cycle into positive one. While this gives us unidirectional current, it is still pulsating and unstable. To fix this, a parallel smoothing capacitor acts as an energy reservoir, filtering the sharp ripples. Finally, a voltage regulator, often employing a Zener diode or integrated circuit, locks the output at a precise flat DC line. By applying circuit analysis to this component, an engineer can calculate the exact ripples factor and load regulation required to ensure that our daily household device receive clean, stable, without overheating or damaging sensitive component. This perfectly illustrates how abstract analog theories translate direct into safe, reliable everyday technology. In conclusion, this project highlights that the operation of modern household electronic device is entirely anchored in the fundamental principle of analog electronic and circuit analysis. Through systematic technical evaluation and mathematical equation, we have demonstrated how individual components such as resistor, capacitor, inductor, and diode interact within complex network to manipulate electrical signal. Whether it is filtering audio frequency in a home speaker system, regulating power inside a smartphone charger, or managing thermal load in kitchen appliances, precise circuit analysis allows engineers to predict efficiency, prevent device failure, and optimize performance. Ultimately, bridging the gap between theoretical analog concept and their practical, real-world execution is what enables the development of safe, efficient, and reliable technology that power our everyday domestic life.